Good. All right. This is a lesson I actually skipped last year, so you're going to be smarter than the calculus students today. Doesn't that feel good? They didn't do graphing cubic functions last year, or the details that we went into on parent graphs. All right, so we're going to look at a lesson on a different type of function. We kind of looked at the graph a little bit yesterday. We started previewing it. Junior, can you read us the essential question, please?
Essential question, how do you graph a cubic function?
Perfect. All right, and then Natalie, can you read us the I can statement? Perfect. All right, so all we're doing is learning how to graph a cubic function today, okay? And as we know, there are lots of different techniques that we're probably going to use, okay? All right, so take a minute to yourself. We're going to look at this explore really quick. Read that paragraph to yourself really quickly. Okay. And this is going to be a little bit of a rehash of what we did yesterday. So a cubic function has to have what term in it? What makes it cubic? Say it louder. I heard it. Somebody at table 3. Say it louder. Yeah, it's got to have that cube on there, right? So this is what makes it, that little guy right there is what makes it cubic. Okay. So a cubic function has to have that in it. It could have a squared term, it could have a linear term, it could have a constant, it could have a mix of those things, but it has to have the cubic in it, and the cubic has to be the biggest exponent. Our next lesson goes into things beyond a cubic, okay? So we can see things that get even bigger than that, okay? So it wants us to complete the table, graph the ordered pairs, then draw a smooth curve through the plotted points to obtain the graph of f of x equals x cubed. We always can default back to a t-chart. If all else fails and you're ever asked to graph something, you can always pick numbers and plug them into an equation. Okay, so that's why we always start here. It's kind of the initial way we learned how to graph is plotting points. Okay, so let's start by putting, we're plugging into the x cubed function. So what's -2 cubed? -8, there we go. Everybody should be answering. You want to participate in your education here, okay? We're going to calculate and graph at the same time. Okay, so while I'm on that one, I might as well go out -2 and down 8. And it gave us an almost nice graph patch there. Okay, when I put -1 in, what's -1 cubed, everybody? Okay, I heard a few more people that time. So -1, -1. All right, I should hear everybody on the next one. You know what happens when you don't hear everybody is Mrs. Ballard makes you do it till I do hear everybody, right? All right. So what is 0 cubed?
0.
Oh, that was better. Good. Okay, let's see if we can get everybody on the next one. All right. What's 1 cubed? 1. We're starting to wake up. Good. All right. What's 2 cubed? 8. Good. All right. So 2 is 8. All right. And then a smooth curve means that we don't have any like jagged points and that we don't have like any gaps. So we're going to draw our nice little curve through there, which should look like what we kind of hinted at yesterday. Looks like a broken parabola, like half of it fell down below the x-axis. All right. Let's take a look at, oh, they did the statements different than I did them on my thing. I thought I was backwards yesterday, apparently. All right, so the domain. So this is a fancy, uh-oh. Gotta love that. We'll see if we can get it back. Disconnecting you now. All right. Oh, and my screen blacked out. Let's see. Connect. There it is. 6, 1, 3, 4. Okay, perfect. All right, so we talked a little bit about all of these things yesterday. They have the domain written a little differently than what we did yesterday, but it means exactly the same thing that we wrote. Okay, so we said yesterday that this was going to go from negative infinity to infinity, right? Um, the other way to say that is all real numbers. Okay. And that fancy R means all real numbers. And if you're going to write the fancy R by hand, you just write like a line through it. Okay. That's the way to write it by hand. All right. What about the range? They did not fill in the range for us. So what was the smallest Y value here? Negative infinity. Good. What's my biggest Y value with the arrow? Infinity. Good. And another way, again, I could have written that as all real numbers. Okay. All right, apparently I was totally wrong in my little setup. Apparently we see it both ways. So the end behavior, remember what is going on at the end. And we talked about this yesterday. So as we're hitting positive infinity, as I'm going this way, what's going on with the Y value? Is it going up or is it going down? Up. So that up, well, how do I write up? Plus infinity, right? Positive infinity. Okay. As we're going to the left, that's what the negative means. So what's going on with the Y? Is it going up or is it going down? Going down. Okay. So what I'm going to write, how do I write that? Negative infinity. Good. All right. So the next thing on here, I'm going to erase some of my scribbles here. Is it talks about the zeros, and this is going to become more important, especially when we go into tomorrow or the next lesson. Okay. The zeros, remember, is where it crosses the x-axis. Okay. There typically are solutions to the equation. So if I was going to solve this equation and set it equal to 0, this would be the solution to the equation. We also call them roots sometimes. Okay. So, and notice it only wants the x value, not the y value. So if we're looking here, our x value at that point is in fact 0. Okay. Then it's asking me, where does the function have positive values? When you see the word value, they're talking about the y. What's going on with the y? Okay. All right. So the positive y values, so if I was just to even like highlight this, positive y values are everything that's here, right? All my y's are positive up here. So that happens when the x is going to the right in this case. So x is greater than 0 is the mathematical way to write that. All right. The negative y values are on this branch, right? So on that branch, we would say that that's where the x value is less than 0. It's really good to make sure you understand greater than 0 is positive, less than 0 is negative. We use it a lot as we keep going through our study of mathematics. Okay. All right. It's asking where the function is increasing. So where is it going up? We basically need to know. So remember, we read it from left to right. This is a good review of last semester. Does it ever go down? No, it always goes up, right? So if it starts going up at negative infinity and it ends going up at infinity. And again, interval notation is fine. Okay. All right. They already filled in the function never decreases. Okay. So this last little bit, I'm not sure if I don't remember if we touched on odd and even last semester. Is the function even or odd or neither? So they kind of give us a hint of what we're supposed to do here. If we plug negative x into the function and we get the original function back, it's even. If we plug negative x into the function and we get the negative of the function, it's odd. If neither one of those things happens, it's neither. Okay, so things don't have to be even or odd. There is a possibility of them being neither. So I'm just going to do some work off to the side. I am going to go Yeah, I'm write it. F of negative x equals negative x cubed. Okay, and remember my original function, I'm going to write my original above here, is f of x equals x cubed. So negative x cubed means I have negative x times negative x times negative x. All right, so what's negative x times negative x? Positive x squared. Good. I'm purposely stepping this out. I know we could do it in our heads, okay? But I wanted you to see the even and oddness here. All right, what's positive times a negative? What kind of sign am I going to get? Negative, good. And then I've got x to what power? Because I've got a squared times a cubed. 3. So do you see how my original function was x cubed, and when I plug in a negative x, I get the negative of the original function? So since I got the negative of the original function, this is odd. Because x cubed equals, I don't know what they're supposed to, I don't know what they want there. Probably negative x cubed. Okay. 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 Let's take a look at, we're still looking at all the characteristics. I'm not going to actually do the calculation. Let's just look at the graph. Okay. The words rate of change. Does anybody remember what that means? Good. That means slope. Good job. So we're basically looking at the slope of the graph. And usually we look at slope with lines, right? When we go to next year in calculus, calculus is the slope. It's really basically the study of slope. It's the slope of curves. Okay. So we're going to kind of look at what the slope looks like between these points on that graph and compare them. Okay. So we're going to look at, let's see, I have a lot of scribbles on there. What have I not used? Let's use this color. Between -1 and 1. So if I were to just kind of imagine a line here between those 2 points versus, we'll use the blue. I don't know. A line between -2 at 1 and 1, 2. So like here, from this point to that point. Ooh, I missed. That wasn't good. Oh, and I erased my line now. That's nice. All right, let's draw that back in. All right, we'll try the negative points again. All right, let me zoom in. So, which slope is steeper? My purpley line or my blue line? The blue is definitely steeper, right? So, because that curve is starting to escalate and grow and grow and grow really fast. Okay. So, let's see if we can do that. So we would say something like the rate of change, and I would probably put in parentheses the slope, okay, is greater on or greater between -1, -2, and 1, 2 than -1, 0 and 0, 1. Okay, you gotta love questions that when they ask them, they give you a definition of something in it. So take a minute on 2 and read that to yourself, please. Read number 2 to yourself. Okay. Levi, can you read just that first sentence up to that green line there?
The graph is said to be symmetric about the origin, and the origin is called the graph point symmetry. If for every point xy on the graph, the point negative x and negative y is also on the graph.
Perfect. Okay. Um, I always my having you guys read is my stab at helping with the literacy that we're supposed to be working on. You guys know RI is coming up in within the next 2 weeks, right? I don't know if English has talked about that or not yet, but you should be tested again. So you have another opportunity to grow. I can't wait to see you guys' scores again. So even though it has nothing to do with my class necessarily directly, but I like looking at the graphs. So they're pretty colors. All right. So it totally defined what symmetric about the origin is, right? Or it's said to be symmetric about the origin. So I would underline symmetric about the origin. And then if for every point x, y on the graph, the point negative x, negative y is also on the graph. So let's demonstrate and see if that's happening. Okay. And in this case, it would say that the origin is called the graph's point of symmetry. Okay, hopefully that's familiar from geometry and earlier math classes. So I'm going to look at this point right here that's on the graph and this point right here. That point right there is the point 1, 1. So in order for it to be symmetric about the origin, I would also need the point negative 1, negative 1. Look at that point right there. It's out negative 1, down negative 1. So we would say that this graph has origin symmetry. We could test other points too, but we would say this one has origin symmetry. So we would want to say f of x equals x cubed has or is symmetric about the origin. Let's go that. That makes more sense. Is symmetric about the origin because both 1, 1 and negative 1, 1 are on the graph. I'll fix that. Got another 30 seconds to write. Look at the next part. Okay. Go ahead and read that to yourself really quick. Read number 3 to yourself. Okay, so I'm going to pull out Desmos and we'll demo it together, okay? So let's look at Desmos really quick. All right, so our first one is I'm just going to put in our parent graph, x cubed. So that's red, okay? And we're supposed to be talking about a reflection. So I'm going to put in g of x equals negative x to the third, but notice it has parentheses on it like that. So let me type that one in. Where's the right thing? Here we go. So g of x equals parentheses negative x, oops, parentheses to the third. Okay. So read what it said again. The graph of g of x equals negative x cubed is a reflection across the y-axis. Okay. So if I look at the y-axis, and remember reflection means it's a mirror image. and I folded this on the y-axis, do you see how the red one would land on top of the blue one, and the blue one here would land on top of the red one? Okay. So now let's look at what the next part says. Well, the graph of h of negative x cubed is a reflection of the crowd. Okay, so let's type in without the parentheses. Okay, that's what they want us to do next. Let's look at that. So, I don't know, h of x equals negative x to the third. What happened? Yeah, it went out to exact. Look at what happened. So there's the blue, right? It went exactly over the top, right? So in this case, okay, because that one was supposed to be a reflection across the x-axis. Basically, if I fold on the x-axis, the red graph would land on the green one, and the green one would land on the red one. Okay, so this one has whatchamacallit, the reflection works both directions. Okay. The reason that happens is, okay, so let's look at the algebra behind it really quick. Okay. So g of x equals, so what this is saying is negative x times negative x times negative x cubed. Okay. I'm sorry, that's not what that says. It just says that. Okay, negative x times negative x times negative x. So let's we've already kind of evaluated that once, right? What's negative times a negative? Positive times that negative is going to be negative, and it would be x cubed. Whereas h of x is already that, isn't it? So basically those transformations were equivalent. Okay, so I would just say the transformations are equivalent. That's why it works. So you have both the x and the y, or the whatchamacallit, both types of symmetry across, or sorry, reflections. All right, that is everything you could ever want to know about a cubic equation. All right. We're going to see if we can get through part of explain 1 here, and then we might save the other part for tomorrow, because I want to show you some. I want to have you play with something that's going to lead into eventually the assignment on this. Okay. All right. And review our parent graphs from yesterday a little bit. Okay. I'm going to, normally I wouldn't skip something that we could read, right? I am going to totally skip over that paragraph because I'm not going to teach it that way. Okay. I'm going to rely a little bit more on a t-chart versus what they're doing with it. But we're going to basically combine transformations together. Let's write down the general form of the equation, because I'm going to use a slightly different general form. I'm not going to require B. Okay. See how there's that B in that funky equation there? We're just going to mess with A. Okay. So let's write our general form down. We can just write it right underneath the chart. So g of x equals a times x minus h cubed plus k. It should look very familiar. Didn't we have that exact same thing when we did parabolas and absolute values? The exact same equation, except that it was said squared instead of cubed. Okay. So we're going to kind of do two things here. We're going to identify the transformations of the graph that produce the given graph of the function. So we're going to try to figure out what happened. And then we're going to actually try to move the graph as well, graph it. Okay, so I gave you the x cubed graph so we can kind of see how it shifts. All right. So as a review, okay, the h, remember, moves it left, right. And remember, you have to swap the sign, okay? The k moves it up and down, okay? The a, I'm going to put I should have squished this in somewhere else. The a tells us if it is a vertical stretch or compression. and then a negative in front is a reflection. I'll give you a minute to make those quick little notes. All right, there's one other thing I want you to label on that original graph that we had there, just so you've got the vocabulary down. Back here, in parabolas, we call it a vertex, right? In a cubic or an odd function, we call that the point of inflection. Let's see, inflection, okay? Because in our equation, we can read our vertex or our point of inflection right out of the equation, okay? Which means I can plot that right away. All right, let's go back here. Okay, so the first thing I'm going to do is I'm going to find my point of inflection. Okay. At the same time, I'm going to kind of try to decide how it's going to move. Okay. So remember, when we come in or out of parentheses, what do we need to do with that sign? Flip the sign. So my point of inflection is going to be 1 for the x. What's going to go on for the y? Negative. This should look really familiar. Okay. It's going to stay the same. So inside, change it. Outside, keep it. All right. If I am going 1, do I move to the left or to the right? The right. So I'm going to translate right 1. Okay. And then how is the y going to move? Am I going to go up or down? And then down 1. And down 1. Okay. What's the 2 in front going to do to it? Do you remember? It's a stretch, right? If it's bigger than 1, it's a stretch. If it's less than 1, it's a compression. So let's remind ourselves of that. If A is greater than 1, it's a stretch. If A is less than 1, it's a compression. Okay, so we would say that it's also going to have a vertical stretch. All right, now, it's probably a vertical stretch by a factor of 2. There's a way to get those other points to move. I think it's easier to just pick some x values and plug them into that and do a t-chart to find where my other 2 points are officially, okay? When it comes time for the quiz, I was really frustrated with Otis yesterday. I'm like, oh, great, I'll make an Otis assignment. They can check it and just move their graphs. It doesn't work. They don't have a cubic in there. They only have a parabola, okay? So I had to come up with something else for homework so it would check for you. So on the quiz, it will be a matching thing. You'll have to match the graphs to each other, okay? But for our purposes and notes, we're going to do a little t-chart. So I'm going to say that we've got x and we've got g of x. And really, I need to pick out 1 point. Actually, let's not do the t-chart. Let's just do 1 point. We're going to use the properties of the graph. Let's just pick a value, okay? We're going to work smart and not hard and be lazy about this. So see how my x value on that vertex is 1? I could go either direction and pick a point. So what number would be a good choice to the left? -1. Okay, what's even better? What's the best number to plug into things? What's easy? 0 would be super easy, wouldn't it? If I wanted to pick a number to the right, couldn't I just pick 2? I like to pick 10 sometimes because it's easy to work with. So I'm going to pick 0. And remember, I just picked that number. Okay? All right, I'm going to plug 0 into that equation. So 2 times 0 minus 1 cubed minus 1. I need to do that arithmetic to find my y. Okay? All right, so we have what's 0 minus 1? -1. Good. I'm doing a lot of steps. You could do more in your head, and that's okay. What's -1 cubed? Good. 2 times -1. -2. And -2 minus 1 is? So my point, 0, -3 is on the graph. So if the point 0, -3 is on the graph, we know that, okay, so I'm going to follow a pattern, okay? Do you see how in my original here, it's up 1 over 1 and down 1 over 1? Do you see that little pattern there? Okay, so I'm going to follow a similar pattern for this one. I'm noticing it is over 1, or down 2, right? So I'm going to go over 1, up 2. You have to know, though, that it's, because it looks like a line, right? You have to know that it's making that cubic path. Okay, so I'm going to erase these guys here. All right, so here comes my cubic. Let me use something else. So I'm going to go curve it up to the point of inflection and then curve it up again. Okay. That's where I'm going to stop the lesson today. We're going to finish this tomorrow. Okay, so it will give you some time to work on homework in class, but we're not done yet. Okay. I want you guys to go into Google Classroom. I posted something yesterday. This is where you need your yellow sheet. Okay. Let me get there too. Because I want you to play with something and kind of learn how to use this thing. Okay. So there's an activity in there that's called Parent Function Marble Slides Intro. Open that up. One person's turned it in already. Nice. All right. And you can just hit Start Activity once you're in there. Okay. Okay. So the idea here is there's 6 problems in here, and I think we had like 5 or 6, maybe 7 parent functions yesterday. And these are literally just the parent functions. So you need to determine which parent function is going to collect all the stars. Okay. And that's where the homework for cubics is going to be something like this. So what parent function does this first one look like here? It looks linear, right? So what's the equation for a parent function for equation of a line? X. So I'm going to type that in. Okay. And then I got to see if I was right by collecting all the stars. So I see that little purple dot? It's like a little ball. Okay. And I hit launch and it says success if I got it right. Does that make sense? Okay. So spend the last 10 minutes. Is it 10 minutes? It's about 10 minutes, right? 57. More than 10 minutes. You guys got a lot of time. I want you to finish off all your, see if you can find all the parent functions based on that. Okay.